Okay, cool. So this is looking like our setup, right? We definitely have a singularity on the real line, yeah? Because just 0 itself is a pole, yeah? So we will consider the integral. I'm going to write C of capital R delta of e to the iz, because we've learned that this is how we get these trigonomic functions, and then z over z squared minus 2z plus 2 dz, where we have a contour like this. So notice that the degree on the bottom is 3, the degree on the top is just 1, right? So in this situation, we do not need to actually use the rectangle. This standard semicircle will work perfectly well for us. So I'm just going to use standard semicircle. Okay, I don't have an language explanation and I feel guilty. So now I'm not changing my mind. I'm now going to use a rectangle because I actually haven't shown you this and it probably isn't as trivial as I said. So let's just do it this way. Yeah, so when we have, let's put it on here. So when we have something like this, where we have P of Z over Q of Z, okay, and we know that the degree on the bottom is at least the degree on top plus 2, and we integrate over the semicircle like this. Well, the length of the semicircle is R, right? And for very large Z, then because the leading order terms of this thing are the dominant players, then this thing will decay like 1 over mod Z squared. Yeah? So P of Z over Q of Z will be less than some constant mod Z squared. We saw this, yeah? For all large enough Z. Yeah? Do you remember seeing this? Yeah? So if we just look at this thing, then we're integrating something which will be less than a constant times R squared. So again, we less than a constant times R to the minus 2 times something of length of R. So then the absolute value of this thing will be less than a constant times R to the minus 1. Yeah? So if we have this property that as we get very, very big, this thing, should be absolute value. This thing decays like R to the minus 2, then a semicircle is fine. Yeah? If we don't have that property, then we have to use special cancellations of our function. So when we considered this thing, e to the iz, P of Z over Q of Z, yeah? The reason this worked is because we had special cancellations allowing this to actually work out for us. When we integrated along here, because we're going along an imaginary line, we would have e to some minus something depending on t. So this thing decays incredibly fast as we go directly upwards like this. Yeah? And as we integrate across here, then because we are far enough away, the fact that p has got 1 degree less than this guy means that integral across this thing here is also negligible. Yeah? So this thing depended very much on this special structure of the cancellations that involved in this thing. And that allowed us to get away with the situation when we have just the degree on the bottom is 1 more than the degree on the top. All right, so backtracking on what I claimed, we are indeed going to play with 3 parameters. We are going to have R, Y, and delta. And we are going to do this thing. Because this thing for sure we saw works, right? This did work for us. So we have this is r plus iy. This is r minus r, and this is minus r plus iy. And then this thing here is delta. Yeah? Cool. So let's deal with this thing. So what do we know? We have that if we take the limit as r goes to infinity, but first we have to take the limit as y goes to infinity of this guy, c of r y delta e to the iz over z squared minus 2z plus 2. Yeah. Then the sides will cancel and the top cancels, so then this ends up being the integral from minus infinity to minus delta of e to the ix x, let's get the right pen, x squared minus 2x plus 2 dx plus, well, if we put the correct orientation, it's going to be minus, if we orient anti-clockwise again, minus this semicircle, this little semicircle right here. This is our guy, c plus delta of 0, like this. And now this is a complex integral, it's integrating around the complex. There's no longer on the real line, so we put this as z, not of x. Like this, dz. And then this integral, delta to infinity, this guy. Like this, yeah? Because of stuff we've learned. We've learned that the sides are not important when we take the limit, first as y goes to infinity and as r goes to infinity. So this is just previous stuff, yeah? Cool. All right, we also know that as soon as we include all the singularities, then this thing is an explicit thing we can calculate. We'll get to that in a second, yeah? If we just look at this thing, and this thing here, then as delta goes to 0, this is exactly going to be the principal, Cauchy principal value. Yeah? So this stuff in the red box is the stuff we want to actually get. Yeah? This is the extra stuff, so we're going to put it on the right-hand side. So let's call this thing star. So then star, no, let's do this better. So then this stuff here that we want to actually calculate, so we're going to put this in proper way. So this is the principal value of this integral, which exactly means this thing is the limit as delta goes to 0 of e to the minus x over x squared minus 2x plus 2. This thing, now this thing is on the other side, and we also know in the limit as delta goes to 0 that this is actually going to be just half of the residue at that point. So this is going to be I times pi, the residue of our function. Let's simplify notation and let's get rid of this. Let's simplify notation and let f of z be this function, e to the iz over this thing, z squared minus 2z plus 2. Okay, so this is the residue at 0 of f. Okay, and then all the other poles. Well, what poles do we have? If we look at the bottom, and let's see what we get when we factorize this. So z minus 2z plus 1 is z minus 1 plus I z 1 minus I. Is that correct? let's check. So multiply this by this, we're going to get, this is not 1, it's 2. We're going to get 2. And if we multiply these guys through, then we are going to get a minus iz. Oops, this is minus. We're going to get a minus iz, and then we're going to get a plus iz. So they will cancel, and we're going to have a minus 1 and a minus 1. So we get minus 2. So yeah, this is correct. Huh? Everybody happy? Cool. So our one pole inside our region is the sky, which is here at 1 plus I. 1 plus I is the one position we have a pole. So we have therefore just 2 pi I, the residue of 1 plus I of f. So the thing we're looking for, or at least what we're looking for, is the imaginary part of this guy, because this is actually our ultimate goal, is given by this thing that we can explicitly calculate now, because it's just a matter of calculating the residues. Everybody happy? Yeah? All right, cool. So, running out of space, let's calculate these residues. So what kind of pole do we have? We have a simple pole at 0, and we have a simple pole at 1 plus I. Yeah? So let's see what happens. So the residue 0 of f is the limit as z goes to 0 of z times this expression, f of z, which is the limit as z goes to 0. This is our function, so it is just e to the iz over z squared minus 2z plus 2. Yeah? And what's that? That thing is just e to the 0, which is 1. And this is just going to be just 2. So this thing is just a half. Yeah? Let's do the other residue. The residue at 1 plus I f, that's the limit as z goes to 1 plus I. And of f of z minus 1 plus I. F of z yeah, and what is this? This is the limit as z goes to 1 plus I. And then this thing will cancel one of these factors here. So the other factor, I've rubbed it off, so I have to try and remember. Let's put it up here so I don't erase it again. So how did we factor this? It was z minus 1 plus I. And then it was z minus 1 minus I. Right? That was the polar, that was the factorization, right? So then when we do this limit here, then we're going to have this factor of z minus 1 minus I just vanishes. So then this will be the limit. I should put it down here. This will be the limit. I already have it here. This will be the limit of e to the iz, and then z, and then z minus 1 minus I is the only remaining factor, right? Because this guy knocks out this guy. Yeah? Cool. And then everything is nicely continuous here. So we can just plug in the value. So then we're going to have just e to the I times 1 plus I. And then we're going to have 1 plus I. And then 1 plus I minus this, the ones will cancel, so that this will just be 2i here on the bottom. Yeah? And then what's this? This is e to the minus 1 plus I. And is there anything we can do with simplifying this? A little bit, I guess. So we can like this. and then that'll be minus 1 plus I. Like this. I don't like that form. I want to put it on top. So let's multiply it by its conjugate, which is minus 1 minus I. Yeah. So if we multiply top and bottom by minus 1 minus I, then we're going to have e to minus 1 plus I. And multiplying this by minus 1 minus I, we'll have minus 2 on the bottom. No, we won't. Let's do that. We will have, so we have minus 1 plus I multiplied by minus 1 minus I will just be 2 on the bottom, right? Yeah, so just be 2 on the bottom, so we'll have 4. And then we'll have minus 1 minus I on the top, and I'm going to write that just as like this. Like this. Yeah? Cool. All right, so that is this residue. And so let's put that together with this formula here. So just sticking it in here. This guy we found out was just a half, right? This is this thing. So we have just I pi over 2. And then this is 2 pi I times this somewhat complicated expression. So I'm going to write pi I over 2. There's 4. Let's put the minus over here. And then we have this expression here, e to the minus 1 plus I, 1 plus I. And what we need to figure out is the complex part of this thing in order to get the right answer. So we have to do a little bit more calculation. So what is this thing? So e to the minus 1 plus I is e to the minus 1 e to the I. E to the I is cosine of 1 plus I sine of 1. Yeah? So if we take, no, I messed it up because I actually want the real part, because this thing here is multiplied by I. So what I actually want is the real part, not the imaginary part. Okay, let's do that again then. Real part. All right, what's the real part of this thing? So the real part, it's when we multiply this by this, we are going to have this thing times this thing. So we have e to the minus 1 cosine of 1. And then this thing times this thing, which now becomes minus. So that seems to be the real part. Yeah? Everybody with me? Okay, cool. So then I wanna not erase. I want to have another board, so I'm gonna erase stuff. So then, what we actually want is the real part. Sorry, the imaginary part of this thing. So let's put this in a box like this, and then the imaginary part of what's in the box. And we're just going to read it off. So it's going to be pi over 2 from this thing, and then it's going to be minus pi over 2, and then times this thing over here. So I want to put it down because it's too long. So minus pi over 2 times, let's put the e over here, 2e times cosine of 1. Pen down. Cosine of 1 minus sine of 1. Yeah. So finally, this guy, which is the thing we were looking for, well, I should write principal value, because it definitely has a singularity. So this thing is equal to this thing, and we are good. This is the correct thing. Okay. Cool. So, looks like we're out of time. Let me just go over the steps. We have some guy like this. We identify that it's got a pole on the real line. So we can't just simply create standard type contour. It's something we have to turn into this trig form. So we're going to write this e to the iz to recover this expression as the imaginary part of this expression. Yeah. We create our contour. We're going to use a rectangle. Yeah. We don't care about the sides or the top because we know the limit as y goes to infinity, then r goes to infinity means that they go away. Yeah. So then, taking the limit as r, y goes to infinity of this thing, yeah, we just end up with the integral from minus infinity to here. So we end up with this thing plus a little bump here plus this thing. Yeah? But we're going anti-clockwise, so as we do this, we notice we're going clockwise around the little semicircle. Yeah? And when we do the calculation, we did it anti-clockwise, so parametrization was anti-clockwise. So we remember, therefore, to put a minus here. This is a minus. Yeah? And then we have the part from delta onto infinity, which is this part. And then we see that this thing is the thing that we want. This is the thing we want. Yeah? So we put this on the other side. And then, if you don't remember it, then hopefully it isn't too hard to calculate. This guy here is just going to be half of the residue at 0. This is the result that we learned. And looks like it's erased. Here it is. So this thing here is the contribution from this guy. And this thing here is just the residues of this complex function inside our contour, and there's only one, it's up here. Yeah? So at this point, if you've got this right, then it's just a matter of calculating residues, which you've had some experience of, you're getting better of. And both of them are poles, so we just multiply them by the factor. So since this is a pole at 0, we multiply by this, take the limit, this one's nice. This guy here is a harder expression. This is the factor we have to multiply by. We get some complicated expression. Finally, get some answer for this. And to save work, we're not going to multiply out this complex number to see exactly what it is, because all we actually want is just the imaginary part of this thing. We want the imaginary part of this thing. So we just need the real part of this thing, not the imaginary part as I originally thought. We just need the real part of this thing. So we calculate the real part of this thing. We multiply together these complex numbers, this one and this one, and we find out it's equal to this. Yeah? And therefore, the imaginary part of this entire expression is this thing, and it's equal to the thing we're actually looking for, and that's how we do it. Yeah? That's how we do it. So apart from this extra little wrinkle of having to avoid the pole, and remembering to put that contribution on the right-hand side, don't ignore it, it's not going to 0, then this is just the same kind of thing we've been doing before. So it isn't that much harder. It isn't that much harder. Yeah.